All right, good morning, everyone. Welcome to Year 11 Physics. Today and this week, we're interested in looking at a bit of a revision. This lesson in particular is interested at looking at a bit of a revision of some of those things we learned in Year 10 about energy, work, and power. So to kick us off with work. In physics, when we think about work, it's about changing energy from one type to another. We think about work as being transformation of energy from one type to another, changing the universe in some sort of way. When we start talking about mechanics, when we talk about mechanical physics, then work is a lot simpler even than that. We say that work is force applied over some distance or displacement. Force applied over some displacement. So if you lift a rock up above your head, you're doing work on the rock. If you push a shopping trolley across the car park, you're doing work on the shopping trolley. So work is measured in joules, just like energy is measured in joules. Work is the expenditure of energy in mechanics. S is the displacement in meters. Force is a force acting on an object, and that's in newtons. So when we think about mechanical energy, energy comes in all sorts of different types. Okay, so what do I mean by mechanical energy? We know that energy comes in many, many different types. We know that energy is conserved, no matter which type of energy you're talking about, as it transforms from one type to another type. Gravitational potential energy in a shot put will become kinetic energy as it falls from your hand onto your foot. Chemical potential energy can become thermal energy as a firework or a firecracker is let off, and maybe even become a bit of light energy. The amount of energy before any sort of interaction is the same as the amount of energy after. When we start talking about mechanical energy, we are focusing in our attention specifically to the energy of a massed object due to its motion, kinetic energy, and the energy of a massed object due to its location in a gravitational field, i.e. potential energy or gravitational potential energy. So these are the two we're particularly interested in with mechanical energy. Movement energy, kinetic energy, a half mv squared, and gravitational potential energy, which you might remember from year 10 as E equals mgh. So kinetic energy is, or we have an equation for our toolbox. E equals a half mv squared. M is the mass, it's always in kilograms. V is the velocity, and it is in meters per second. Gravitational potential energy, mg delta H. Mg delta H. Very often we just write mgh. It's not a big deal. It's important. We put the delta in there sometimes to remind us that it's not the absolute height. We don't have an absolute height in year 11. We have a relative height. So when we talk about the potential energy, it's actually the gravitational potential energy relative for that body to some other location. For example, if you are holding your little brother up high and giving them a bit of a shake, then it's their gravitational potential energy relative to what they would have on the ground. And that very, very quickly changes if you're holding them above the ground or if you're holding them out the window. Suddenly the gravitational potential energy is a very, very different value. Power is the rate at which we expend energy. It's how quickly we expend energy. And power is measured as work per unit time or joules per unit second. This is power. So that's, now you may not have gotten to power in year 10. It's always a struggle, always a push. In year 10, particularly with your extension classes, you've got so much to cover in biology, in human biology, in geology, in chemistry, and in physics, that by the time you get to the end of your physics studies, it can actually be a bit tough to really get a few good power questions in there. So in any given year as a year 11 physics teacher, we know that the students are going to come in with varying degrees of understanding of power. Power is how quickly energy is consumed, work per unit time. Some examples. A load of 500 newtons is raised 0.5 meters by a pulley. Now, what is this load? The load could be anything that you can imagine. It could be a young person. A 50-kilogram young person would approximately have a weight of 500 newtons, approximately. A 50-kilogram young person. A sack of potatoes, a large sack of potatoes, might have a weight of 500 newtons. So this load of 500 newtons is raised 0.5 meters by a pulley and lever system. The engine powering the system uses 485 joules of electrical energy in doing so. Calculate the efficiency of this electrical energy, of this electrical engine. All right, so can we see the question? Let's talk about what's actually happening here. We have some sort of engine. It says that it's chugging in 485 joules of electrical energy. Okay, we'll accept that. Okay, so 485 joules of electrical energy is going into the engine and it's doing work on this load. This is a 500 Newton load. So if the load is lifted at a constant velocity, then the tension in my cabling is going to be 500 Newtons. We're going to do work on this load. And one of the first things we see is that the work done on the load is equal to force multiplied by displacement. So as we lift it up 0.5 meters, we've done work on the load. Let's talk about that. So we've done some work on the load. 250 joules of work is done on the load. 485 joules of energy was absorbed by the engine to get this job done. So how efficient is the engine? It's that classic concept of efficiency. How efficient are you in your spelling quiz? If you get 250 of the words in your spelling quiz correct out of the 485 words that were in the spelling quiz, that's a big spelling quiz, then what's your efficiency? What's your score? What's your percentage? That's how we figure out the efficiency. This, I think it's called eta, is our symbol for efficiency. It's got a little nose on it like an elephant. Eta. Look that up. Check that I'm correct. 51 point. All right, 51.5% efficient. So engine is 51.5% efficient. So we have another question. An engine has a power rating of 5 kilowatts. How long will it take to move a crate 80 kilograms, 10 meters horizontally against the frictional force between the crate and the floor of 450 newtons, assuming that the engine is 100% efficient? 100% efficient. Let's have a look at that one. All right, we've got a 5 kilowatts engine. Now, what we mean by a 5 kilowatt engine is that it absorbs 5,000 joules per second. Absorbs. It does not mean that it does 5,000 joules per second of useful work. It does convert 5,000 joules per second of energy into something else. In this particular case, because it's said to be 100% efficient, it will actually convert all the incoming energy into useful energy. But that is not a guaranteed thing. When we see that something's got a power rating, that means the energy in is 5,000 kilowatts in. Doesn't have to be 5,000 kilowatts of useful stuff out. In this case, it is because it is a 100% efficient engine. We want to know how long is it going to take to move this 80 kilogram mass across the ground, 10 meters. It's working against the constant friction of 450 newtons. So the force being applied is 450 newtons. Let's see what we've got. So power equals work over time. What's the work being done? Force multiplied by distance. We know that the power is 5,000. So we've got 5,000 watts is equal to 450 by 10. So that's 4,500 divided by T. And I think that's going to be, what's that going to be? 0.9 of a second. Can someone check for me? Yeah, 0.9 of a second, which is really quick, really quick. You don't want to be in the way.